Hello there, I'm Khalidul, and in this video we will talk about how to create a perfect crystal of copper, which is a face-centered FCC lattice, and I will be using a MATLAB script, but however this can also be used in Octave. This same script can be run on GNU Octave, which is a free open source software that you can also access online for free on websites. And another thing I want to talk about is why am I using this complicated script to generate a simple structure such as face-centered cubic? The reason I'm doing this is I'm showing a general procedure of making structures using MATLAB, and you can follow this procedure to make even more complex structures such as graphene and maybe alloys where you have one atom in the face and another atom in corner, etc. Structures that you cannot generate on simple lamps or atom scale, etc. So for those structures, this sort of strip will be very helpful. So without further ado, let's get started. Before we get started, we need to have some idea about crystallography. So this is a face-centered cubic lattice, and most metals, including copper, are arranged. The atoms in a perfect crystal of copper and most metals are arranged in a face-centered cubic lattice like this. So you have 1, 2, 3, 4 atoms at each corner of a face and one atom at the face center. So you can see here corner atoms, face atoms, corner atoms, face atoms. Now to make this structure, we have to first visualize the coordinates. All right. So if I think that this is the x-axis, this is the y-axis, and this is the z-axis, then this point, this corner atom will be 0, 0, 0, right? So this corner atom is 0, 0, 0. And then this is the lattice parameter of a crystal. So this coordinate will be, for example, the first, each corner will be, let's say this corner will be L lattice parameter, comma, 0, comma, 0. And 0 in the y-axis and 0 in the z-axis, but L in the x-axis. And similarly, again, this corner will be L in the x-axis, L in the y-axis, but 0 in the z-axis. I'm not going to draw all the coordinates, but if you go into it, you will see that there's a pattern. Okay, so for the corner atoms, all the coordinates, the x, y, and z, are either L or 0, and there are all combinations of them. Okay, so there is L00, LL0, there's 000, there's this coordinate will be LLL, and so on. So keeping that in mind, now let's go look at the face atom coordinates. So if I take a look at this face atom, it will be x L by 2. In x-axis it is L by 2, and in y-axis it is 0, and in z-axis it is also L by 2. Okay, and similarly for this one, the z-axis will be L by 2, the y-axis will be L by 2, but the x-axis will be 0. So you will see that all the face atoms are ultimately nothing but different permutation combinations of L by 2 and 0. Okay, so now that we have established what the corner atom coordinates are and the face atom coordinates are going to look like, let's get to the code. So first of all, I'm doing a clear close all CLC, a typical MATLAB command, and to clear the workspace variables, close all closes any figures that are open, CLC clears the command window. Then we have latp equal input lattice parameter A, and xlen equal input x, ylen equal input y, zlen equal input z. This will just take inputs the values of the lattice parameters, the length of the x-axis that your unit cell need to be, or rather your full structure needs to be, the maximum x coordinate, the maximum y coordinate of your structure, and the maximum z coordinate of your structure. So if we give these three inputs, this code will generate a rectangular cuboid structure of x, y, z dimension, and with a lattice parameter of whatever lat p, lat underscore p. Okay. Now n is equal to, what is this? N is equal to ceiling of this is the ceiling function. What's the ceiling function? What the ceiling function does is it does something like this. Ceiling of 2.5 is 3, ceiling of 2.1 is 3. You get the point. All right. Then let's get rid of these. Okay. Now inside you can see max of bracket xlen, ylen, zlen. So this is taking the maximum of these three out of these three variables. So what max does is max, for example, max of 1, 4, 5. What this will do is 5 because the maximum value is 5. It's just simple. It gives the maximum value among these variables xlen, ylen, zlen. So I got the maximum value among these lengths. So what's the highest length you have got? Which length is the highest? And then I've got divided by lat p. So if the highest length is x length, let's say it is 100, then I divide it by the lattice parameter. Let's say that's for copper 3.61. So what this function will do is something like ceiling of max of all xlen, ylen, zlen will be your x length if this is the highest. So ceiling of 100 by 3.61 in case of copper, and so the value will be 28. So this code will make n is equal to 28 means this code will make 28 crystal lattices. Okay, 28 crystal lattices, and then in x direction, 28 in y direction, and 28 in z direction. It will make 28 crystals in all directions. Now let's move to line 7. Line 7 says corners 0 colon lat p colon n into lat underscore p. What does this do? For example, 0 colon 5 colon 20. What this does is 0, 5, 10, 15, 20. So 0 colon lat p colon n into lat p. That, for example, 0 colon 3.61. This will look like this for copper. In colon n 28, like I said, into 3.61. So this will look something like this. It will be 29 variables, 0, 3.61, double, 3.7.22. These are the possible values of the coordinates of the corner atoms. Because as we saw, the coordinates of the corner atoms can only be either 0 or L. For the next lattice, the next unit cell, it will be 2L. For the third unit cell, it will be 3L. For the fourth unit cell, it will be 4L along x-axis. So these are the only possible values of the corner atoms. So I'm calling this vector corners. Okay, I will generate the coordinates from this vector. And then similarly for faces, 0.5 into lat p. So faces starts at something like 0.5 into 3.61 colon, it also increases by lat p, and it goes up to n plus 0.5. So in this case it will be 28.5 into 3.61. So what this does is it starts at half of 3.61, which is 1.8050, and then it increments by 3.61 because each face atom will be separated by one lattice constant, right? Just like each corner atom is separated by one lattice constant, each face atom will also be separated by one lattice constant. But as you can see, it creates up to n plus 0.5. So it will create up to n crystal lattices and then half more. Okay, so if the value of n in 6 is 28, the structure you're gonna get is 28.5 unit cells in this direction, 28.5 in this, and 28.5 in that. But we don't want that, right? We want the xlen, ylen, zlen. So we will cut that structure later in this code. Okay, now let's go to line 9, and you can see xyz equal mesh grid corners, corners, corners. Now mesh grid is a very interesting function. This is the function that makes this code much faster than using a traditional for loop of I equals 1 to x direction, y direction, z direction, and so on. So how does mesh grid work? Well, for example, if you have a equals 1 colon 2 colon let's say 10. So you have a equal 1, 3, 5, 7, 9, and maybe you have b equals all the even numbers, so 2 colon 2 colon 10, and 2, 4, 6, 8, 10. Now you want to make coordinates out of a and b. So maybe the coordinates will be 1 comma 2, 1 comma 4, 1 comma 6, 1 comma 8, 1 comma 10, and then 3 comma 2, 3 comma 4, 3 comma 6, 3 comma 8, 3 comma 10. That's how coordinates work, right? So this mesh grid will do this for you. The way to do that is, let's say x comma y is equal to mesh grid of a comma b. Now mesh grid will generate x and y, two matrices of 5 by 5, okay, and as you can see x is 1 1 1 1 1 2 2 2 2 2, sorry, 3 3 3 5 5 5 7 7, and so on. And also the length of x is 5 times, and the length of y is also 5. So what you should do after that is, I don't want matrices, I want them as columns. Okay, so I want x colon is equal to x is equal to x colon. So what colon will do is it will convert the 5 by 5 matrix into a single column vector. Okay, and then y equals y colon, so it will do the same for y. And then I want to see, let's say, chords, I want to see the coordinates equal x comma y. And then what this will do is, if I look at the chords variable, you see 1 comma 2, 1 comma 4, 1 comma 6, 1 comma 8, and so on, and 9 comma 6. So all the possible coordinates, the 25 possible coordinates that can be generated using these values are in this chords variable. Okay, all right. So now what are all the possible coordinates of the corner atom? Like I've already said, all the possible coordinates of the corner atoms will be like 0 comma L comma L, or 0 comma 0 comma 0 comma 0, L comma L comma L. So it will all be called combinations of 0 and L, all of which are included in the corners vector. All the possible 0 and L's and their multiples are included in the column vector of corners, right? So if I say x comma y comma z equal mesh grid corners corners corners, so I'm using the corners variable thrice, okay, because x direction corners, y direction corners, z direction corners. So what this will do is this will generate all the possible corners. And to simplify this, let's say we know in one unit cell there is how many corners? 8 corners, right? For example, as we saw here, 8 corners, 1 2 3 4 5 6 7 8. So let's see if this does make it 8 corners for a single unit cell. So I will execute the line up to this line, up to line 13, so that I get x pose, y pose, z pose. And if I execute this, so it will ask for lattice parameter 3.61, and I want just one unit cell, so my x length will be the same as lattice parameter, so 3.61. Y length will also be that, z length will also be that. And once I execute up to this, you can see x pose. So if I want to know length of x pose is indeed 8. So x pose is, see, 8 coordinates in it, 8x coordinates, 8y coordinates, and 8z coordinates. And in fact, now if I just make a scatter plot, so scatter 3 of x pose comma y pose comma z pose, and for clarity I want the scatter plot to be filled, so I can see that all the corner atoms are generated. You can see that here. All right, so if you look at it from the front, from the xy view, you can see 0 0, 3.60, and this is one face, this is another face, and this is another face. So all the faces are identical, and if you just rotate it, you can see the corner atoms, the 8 corner atoms are generated. Clear? All right. Now for the more complicated part, that is the face coordinates. Now how do I do the same thing with the face coordinates? Now you see, the face coordinates can be any combination of corners and faces, because if you look at here, for example, for this face atom, the coordinate is L comma L by 2 comma L by 2, right? X direction L. So X direction is a L, which is a corner vector, which is part of the corner vector. And Y direction is L by 2, which is part of the face vector. And Z direction is also L by 2, which is also part of the face vector. And if you see this, this is also 0 comma L by 2 comma L by 2. And if you take this atom, this is also part of the, this will be what? In X direction, this will be L by 2, so a face. In Y direction, this will be a corner, L. And in Z direction, this will be a face, L by 2. So if I take every possible combination of corners and faces, 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 corners, corners, faces, faces, and faces, corners, faces. If I take all the possible combinations, then I will have all the possible all the possible face atoms in this part as well. Clear? All right. Now that this is done, and after all the expose is done, I will just I just renamed the variables. Basically here I stored x pose as x, y pose as y, and z pose as z. Now for the deletion, because we need to delete some, all right, because clearly we made the structure too big at first, because remember, whatever the x line, y line, z line, we just took the maximum and made a box of this many unit cells by this many unit cells by this many unit cells, a full box. So I don't want to do that. I need to cut that. So I need to find the coordinates that I want to delete. There are coordinates that I want to delete. So which coordinates do I want to delete? So x del is equal to find x greater than x length. So whichever x coordinates are greater than x length, I will find those. What find does is it finds the indices, like maybe the fifth coordinate is x greater than x length, so the value will be 5, and maybe the seventh one and the value will be 7. So what find does is it finds the indices of those atoms. And similarly I do it for y del and z del. So which atoms are beyond my x bound, which atoms are beyond my y bound, and which are beyond the z bound. I found their indices. Now I'm making a matrix of chords equal x comma y comma z. So x is the first column, y is the second column, the x coordinates and the z coordinates are the third column, and so on. Now chords of x del colon y del colon z del. So all the chord indices that exceed the x limit, all the indices that exceed the y limit, and all the indices that exceed the z limit, all of them are concatenated concatenated in one after another, all right, as rows, and all these rows will be equal to nothing, just empty brackets. What empty brackets does in MATLAB is it just deletes that row. For example, if I write a equals 1 colon 5, it does 1 2 3 4 5, and now if I say a of 2 is equal to empty brackets, this will just delete that a. So now if I say a 1 3 4 5, so it just deleted the second coordinate, the second value of a. So this, what line 37 does is it will delete all the rows that satisfy these conditions, that is, they exceed the limits set by the user in x len, y len, and z len. Now again I take from the chords variable back to x, y, z, and I can make a scatter plot of x, y, and z. Now if I make this scatter plot 3.61, 3.61, 3.61, I'm just making single unit cell first for better visualization. So you can see this is all the corner atoms we have already previously seen, but now you can see this is the face atom for the bottom face. This is the face atom for the XY YZ face. This is the face atom for the XZ face. This is the face atom for the YZ phase, other YZ phase, and so on. So you can see that this is identical to what we expected, what we desired, that is 1 unit cell. Now, this same code can be used to make as large a box as we want. So if I just execute the same code again with lattice parameter 3.61 and maybe 100 by 100 by 300. So what I get is, so as we can see, this is 100 by 100 by 300 cuboid of copper atoms. All the blobs are copper, each copper atom. And although the ratio is not correct here, so we can fix that with axis square to make the axis actually proportional ratio. And that is it. You have just generated the 3D coordinates of a perfect crystal of copper atoms arranged in a face-centered cubic FCC lattice. In the next video, we will see how to save these generated coordinates into a LAMMPS readable data file and then use that to carry out a tensile test on this particular copper structure and figure out or rather calculate the elastic properties of copper. If you would like to watch that, be sure to subscribe to the channel, turn on notifications, hit the bell icon, and be sure to hit the like button. And if you want to follow my research work, my Google Scholar profile and LinkedIn profile will be linked down below. You can also follow me on Facebook, Instagram, Twitter. They are all linked down below. And even I take online physics classes. If you would like to join them, the form will also be linked down below. And that is it. Thanks for watching. I hope this video helped you. Bye bye.